The following content is provided under a Creative Commons license. Your support will help MIT OpenCourseware continue to offer high-quality educational resources for free. To make a donation or to view additional materials from hundreds of MIT courses, visit MIT OpenCourseware at ocw.mit.edu.
All right, so you guys have read all about method of weighted residuals, yes? It makes perfect sense. Yes? We need to go through things today? A little bit? Okay, just a little bit. Yeah. All right, so actually, before we do that, I want to let's just put up the list of topics that we're going to talk about today. So I want to start by just talking about the measurable outcomes for the module, remind you of what it is we're going to do. Then we're going to introduce the model problem. You read this in the pre-class reading, but it's the steady 1D diffusion. And we'll do a few things in general, but more or less we're going to develop the theory by thinking about this specific example. We're going to talk about the idea of approximating the solution with basis functions, which is a fundamentally different way of doing the approximation compared to what you've already seen in finite difference and finite volume. Then we'll look at the collocation method. And then finally, we'll get to the method of weighted residuals. Okay, so what I'm going to do on the board is more or less paralleling what's in the notes. And so I can go quickly on the parts that are already clear, and we can spend more time on the parts that you have found to be confusing. Okay, so I'm not going to put the screen down because it'll take a while to get the projector on, but I just want to remind you that there's the measurable outcome list. It's embedded on the MITx site. It's also on the mitosis.mitx.mit.edu site. And so we're into a new module now. There are 4 modules in the class. The first one was integration methods for ODEs. The second one was finite difference and finite volume methods. We're in the third one now, which is the finite element methods for PDEs. And so I think it's really helpful for you to go back and, to go forward at this point and look at the outcomes and think about specifically what it is you're going to have to be able to do, because as you are going through all the notes, and I know there are a lot of notes for this section, will help you think about what are the specific skills that you need to take away. There'll be homework problems in the project that will help you do that too. But, you know, for example, describe how the method of weighted residuals can be used to calculate an approximate solution to the PDE. We're going to cover that today. Then be able to describe the differences between the method of weighted residuals and the collocation method and the least squares method for approximating a PDE. So there's a lot of really specific outcomes. I think there's probably about 12 outcomes that are associated with this module. Go and take a look at them, and I think that'll also help you divide up the material and think about what it is that you need to be able to do. But let's start off by thinking about our model problem. So a model problem just means a simple problem that we're going to use to develop things on. And so the model problem, again, is steady 1D heat diffusion in a rod. And the PDE should be pretty familiar to you by now. It's d by dx of k dt dx equal to minus q. We're thinking about a 1D domain. So here's our domain. That's the x direction. The domain is going to have length L. So we'll have x in general going from minus L over 2 to plus L over 2. The k sitting in here, in general, is going to be a function of x, although you'll see that just to make things simple in the beginning, we'll will at some point make K constant. That's the thermal conductivity of the material that the rod is made out of. And this Q on the right-hand side also can be a function of X, is the heat source, and it's actually the heat source per unit length, to get the units right. Okay, so simple problem setup, PDE, specified heat source. We're also going to need to apply boundary conditions when we actually get to specifying a particular problem. So there's one particular problem in, that we will use, one that we can compute the analytical solution for it, because if we can compute the analytical solution, we'll be able to look at errors and things when we look at the numerical approximations. So for the particular case where K is a constant and equal to 1, the length of the rod is 2, so that X goes from -1 to +1, and the heat source is Q of X being 50 e to the X, and again, this is the same example that's in the notes. And boundary conditions, the temperature at the right end of the rod is set to be 100, and the temperature at the left end of the rod is set to be 100. Okay, so for that particular case, we have an analytical solution that you could get by integrating the PDE, and that turns out to be T of X is -50 e to the X plus 50x, the hyperbolic sine of 1, plus 100 plus 50 times the hyperbolic cosine of 1. Okay, so that's just what comes out of this analytic setup, and that's maybe a little bit hard to think about. So let's just sketch what T of X looks like as a function of X. So there's X going from -1 to 1. If we stick in X equal to 0, then, X equal to -1, then we should be getting the boundary condition back. T is 100. So if we make this 100 on my t-axis, then the solution looks something like this, and it comes back down to 100 at the other end. Okay, so that's an analytic solution that we can compute. And again, we're just doing that because when we start looking at numerical approximations, we're going to want something to compare to. So a simple problem where we can actually integrate things analytically. Okay? Yep. I don't think I've told you anything. All right, so let's now start thinking about the solution approximation. Everybody has... Again, everything I'm writing is scanned in online, so I know it's good to copy stuff down and help follow along, but also you will have copies of the full notes. So now let's start thinking about this idea of approximating the solution. So first, let me ask, if we were going to solve this problem using finite differences, what would we do? We'd run to Alex and ask him to help us. What would we do if we wanted to solve this problem using finite differences? We'd break up the domain into a bunch of cells, and then what? How would we approximate things in the PDF? Yeah, good. So we would decide what kind of a scheme we wanted to use, and we would approximate the derivatives. And that's kind of the key part of what you said, right, is that we would take this, we've set k equal 1 constant. So basically we've got a second derivative of t sitting here. We would approximate it using our favorite finite difference stencil, maybe the central difference for second derivative. So I think it's really key to keep in mind that finite element departs from that mentality right from the beginning. that with finite elements, we're not going to approximate the derivatives here. We're not going to approximate this operator, this d squared by dx squared that's acting on t. The finite elements, we're going to assume a form for the solution t. We're going to approximate the solution. We're going to assume a form for the solution t. We're going to substitute in and do a bit of mathematical magic, and then solve to find certain attributes of that solution. Okay, so it's already quite different to finite differences. So how do we get started? We start off by, and let's call this 2a. We're going to say, to approximate the solution, let's use a sum of weighted functions. Okay, we know that t is a function of x. T varies continuously along the domain here. It's a function of x. That's an infinite dimensional problem, right? T is a continuous function. Let's rather write our approximate solution, which I'm going to call t tilde of x. So this guy here is the approximation of my exact solution, t of x. And I'm going to write it as, I'm just going to leave a bit of space here, the sum from I equals 1 to capital N of some ai's times some phi's that are a function of x. And what are these guys here? These things here are known functions. They're things that I'm going to specify. And what you'll see is that these things are going to be referred to later on as basis functions. So these things are known functions of x. We're going to specify them, the phi's. There's n of them, capital N of them. And the ai's here, these are unknown weights. Okay, so what I've said is that t of x, an infinite dimensional problem, t is some continuous or some function, might be continuous, some function of x on the domain. Let's approximate it as a finite sum from I equals 1 to n of some weights or some coefficients, ai, just constant, times some functions that we're going to specify. So can you see that we've discretized the problem in a different way than we did in finite differences? We've discretized the problem because now we have how many unknowns? N. We have n degrees of freedom, n unknowns, these ai's that we can use to create our approximate solution. And I left a bit of space here because I'm going to write this in. I'm going to write in 100 plus that expansion. Why do you think I wrote the 100? I heard the B word. The boundary conditions. Yeah, in this particular example that we're considering, the boundary conditions, Dirichlet conditions are specified to be t equal 100 at either end. So let's put the 100 out in front, and then the rest of it there, the sum of the ai times the phi's is going to satisfy zero temperature at either end, right? Okay, so in this particular example, this guy, this 100, is chosen to satisfy our boundary conditions here for our model problem. Okay, so by writing this, and this sort of approximation of the temperature, it's a simple equation, but I'm spending a little bit of time because it's really important it's clear in your mind, because this is really kind of it's the first key step of making this approximation. We've turned the problem of determining t tilde of x, the approximation, which again is really an infinite dimensional problem, into the problem of determining the coefficients, the A1, A2, up to AN, where we have now just capital N unknowns. Kevin, yeah. Yeah, so if you had like 100 here and 200 somewhere else or something, There's various ways that you could handle it, and we'll talk, and probably in 2 lectures times, about how to do boundary conditions in the finite element method. Sort of, but one approach that we could use just with this simple idea here is you could, for example, have a linear function that went from 100 to 200 and then plus the rest, right? So you could still get the boundary conditions back. But yeah, we'll talk in once we've been through the theory about how to handle boundary conditions more generally. Yeah. But generally speaking, we will do something so that those PIs will satisfy 0 homogeneous boundary conditions. Yeah. Okay, so now the question that you should be asking yourselves is, what are these? I said they were known basis functions. They're things that we specify. So have you guys have seen this kind of idea, this expanding a solution as a sum of weighted functions? You've seen that before, right? When have you seen it? Fourier series, good, yeah. So, I mean, this is no different really to Fourier series, right? What are the PIs in Fourier series? Sines and cosines of different frequencies. So the idea of decomposing a signal into a sum of harmonic components, I mean, signal processing, the entire field of signal processing kind of hinges on that idea. Here we're not going to use sines and cosines, we're going to use polynomials. So phi of x are going to be polynomials in x. In other words, phi are going to be constant plus maybe a linear term in x plus maybe a quadratic term in x and so on. And the reason that we're going to use polynomials is because that sets the groundwork for the finite element method. Okay, finite element method works with polynomials, basis functions, so we're going to start off by thinking about polynomials. Okay, good, straightforward, right? Easy, yeah. Okay, so let's just be more specific for our particular example of what we want to choose for the PIs. And again, I want to be clear, there are many choices for PI, and this is sort of a decision that you make. So this is 2B, choosing the PIs. So again, here we're going to use polynomials, and that's because we're interested in the finite element method, and you will see on Wednesday exactly what the basis functions look like in finite element. But for now, not yet the finite element, we need basis functions that satisfy the boundary conditions, but because we subtracted off, or because we added in the 100 here, you can see it's what I was saying earlier. We're going to set these guys now to be 0. So they're going to be 0 at the ends of the domain, right? So I said we're going to choose polynomials. So what's the simplest polynomial we could choose? We could choose p equal constant. That's not very sensible. What's the next one? X plus b. You could choose a linear function, but what's the linear function that satisfies this condition? 0 everywhere. So that's not very useful. So it turns out that the first one that would give us anything, what's that? Yeah, the first one that would give us anything interesting would be quadratic, or a parabolic function. So we'll choose a quadratic function, and again, there is a variety of things we could do, but here's one. Here's a quadratic function. Well, actually, maybe there's only, well, it could be scaled. 1 plus x, 1 minus x. That's a quadratic. So C1, the first basis function in our expansion, the function of x, and I've written as 1 plus x, 1 minus x. That clearly satisfies the boundary conditions, the 0 boundary conditions at either end. Yep. And then let's also look at a cubic. So that's going to be our second one. And there are a variety of cubics we could choose, but let's choose the one that does x, 1 plus x, 1 minus x. And again, clearly if we satisfy x equal, if we substitute x equal minus 1 or x equal 1 in there, we're going to get phi2 equal to 0. So if we sketched out physically what these guys look like, we sketch phi as a function of x, then the quadratic looks something like that, and the cubic looks something like that. So that's phi1 of x, and this is phi2 of x. All right, that's 0. Okay, so those are the choices we make. And so in this simple example, we're going to use only 2 degrees of freedom to describe the approximate solution. And with those 2 degrees of freedom, what is our approximation? Our approximation is T tilde of x being 100 plus that sum, which in this case is going to be A1 times phi1 of x, where phi1 is 1 plus x, 1 minus x, plus A2 times phi2 of x, where phi2 is x, 1 plus x, 1 minus x. Okay, so physically we're saying the solution is 100. So first of all, just shift it up, 100, then take some amount of a function that looks like this, plus some other amount of a function that looks like this, add them together, and now we're going to say what are the right weightings, what are the A1s and A2s that we should choose so that the function that we get is somehow reasonably a solution of that model problem that looks something like this. Yep. And that's now what we're going to talk about with numbers 3 and 4. The collocation method and the method of weighted residuals are 2 different ways that we can come up with the conditions to help us choose A1 and A2 so that in different ways we get a solution that is a good or just a different kind of an approximation of the problem we're actually trying to solve. Okay? Yep. All right, any questions so far? Questions based on things that are in the notes that weren't clear? No? All right, so that's kind of the easy part. So now let's talk about the 2 different ways that we can come up with conditions that will let us solve for A1 and A2. And the first one is going to be the collocation method. So number 3, collocation. Collocation. Okay, so again, what are we doing here? We're saying for the approximate solution, T tilde of x being 100 plus this expansion, I equal 1 to n of ai times the phi of x, where we're, in our simple example, choosing n equal 2, and the phi is to be these 2 guys here, quadratic and the cubic. We need now to determine the AIs, A1, A2, up to AN, in this case, just A1 and A2. Okay, so first question, how many conditions do we need to come up with? 2, yeah. In general, n conditions, right? We have n unknowns. We said that over here. We turned our infinite dimensional problem of solving the PDE into a problem with n degrees of freedom. So now we somehow need n conditions. And in this example here, where we have just 2 basis functions, we need 2 conditions that will let us solve for A1 and A2. So what does collocation say? Collocation says, let's pick n points. Let me draw my rod back up here from L over 2, minus L over 2 to L over 2. Let's pick some points. In particular, let's pick n points, or let's pick 2 points in the domain, this point and this point, and let's enforce the PDE at those points. Let's make sure that the PDE is satisfied. Remember what the PDE is? d by dx of k dt dx equals minus q. Let's have the solution satisfy the PDE at those points. Okay? And by forcing that, forcing the PDE to be satisfied with the approximate solution at those 2 points, we're going to get 2 conditions, right? 2 mathematical conditions, 2 equations, 2 unknowns we should be able to solve. So that's the idea with collocation. You guys have seen, did you guys see collocation in aerodynamics? Vortex lattice, yeah. What do? You have the collocation point at, which I always forget which way it is. You have C over 4 and 3C over 4, right? Quarter chord point and 3/4 chord point. At 3/4 chord point. So it's the same idea. The collocation point is the point at which you enforce the condition. Yep. So it's exactly the same idea. Okay, so how does that work out mathematically? So that's what collocation means. We're going to enforce the PDE at endpoints. Okay, so how are we going to write that? So let's again write down the example that we're considering, which is the 1D heat equation. And I'll write it in the general form here with K still in there. What's d by dx of K dt dx equals to minus Q. Okay, so now we are going to define something very important, which is the residual. And this is a really important concept that we're going to use repeatedly all the way through this finite element module. So what is the residual? We're going to call it capital R. It's going to be a function of our approximate solution, and it's a function of x. And for this 1D heat equation, what's the residual? It's d by dx of K dt dx, dt tilde dx, plus Q. Okay, so 1D heat equation, d by dx of K dt dx equals minus Q. The residual for that equation, R, which is a function of the approximate solution, T tilde. So if you want to mark that this is the approximate solution to remind yourself. Function of the approximate solution and of x is d by dx of K dt tilde dx plus Q. So does someone want to give me in words, what is the residual? Give me some words to describe it. Yeah, good. The amount, so the residual is the amount that the approximate solution doesn't satisfy the PDE. In other words, if we come back to our original PDE, we brought everything over to the left-hand side. So it would read d by dx of K dt dx plus Q equals 0. Then if we take instead of the actual solution, if we take an approximate solution, T tilde, we substituted it in, the residual is how much we get that's different from 0. So it tells us by how much the approximate solution, T tilde, does not satisfy the governing equation. Yes? So someone tell me, how is the residual the same thing as the error? If I define the error to be the difference between the exact solution T and the approximate solution T tilde, is the residual the same thing as the error? Not the same thing. So how is it different? Yeah, so let's think about that. So if we define the error to be T minus T tilde, this is the error. Is this thing a function over the whole domain? Is E a function of x? Yeah, right. So E is a function of x if it's T of x minus T tilde of x. Yeah? How about the residual? Is the residual a function of x? Yeah, so they're both functions that we could plot over the whole domain x. We could plot E of x and we could plot R of P tilde comma X. So they're both functions that are defined over the whole domain. But they're measuring different things, right? Yeah, that's exactly right. The error is measuring how wrong is T of X. What's the error in T? But the residual is measuring how far is the equation from being satisfied. What's really amazing about the residual? Yeah, exactly right. Which is real, isn't that cool? And that's kind of, I mean, I think in a way that's kind of like the amazing breakthrough here is that, yeah, we'd love to know the error, but if we knew the error, we would know the true solution. So then why would we be doing all of this? The really cool thing about the residual is that we don't need to know the true solution. We can take our approximate solution, we know the equation that it should satisfy, and we can measure how far off it is. Now, just because the residual is small doesn't mean the error is going to be small, and that's a whole kind of field of study depending on the PDE that you're studying. For this particular PDE, it turns out the residual and the error will be nicely related, but if you have a nasty PDE, the residual might not be a good indication of what's going on, but it's still a very powerful thing that can give you a sense of how good is your approximate solution without actually knowing the truth. And we're going to use this idea of a residual over and over and over again because we don't need to know the actual solution. Yeah. Sometimes I know the residual can be something that gets people tripped up. Is it kind of, it's pretty neat, right? Take the approximation, substitute it into the PDE and see how well you're doing. Not the same thing as the error. So one thing, no, that's not the same thing here, but one thing we do know is that what happens if I substitute in the exact solution here? Residual is 0 everywhere. Yeah, okay. All right, so how is that going to help us with our collocation method? So we defined the residual, and what we're going to do, maybe you can see now what we're going to do with the collocation method is when I said we enforce the PDE at end points, what we're going to do is we're going to set the residual to be 0 at end points. In other words, we're going to pick n, in our case, 2 values of x, right? So remember we said that the residual was a function of x, something. We're going to pick 2 values of x. We're going to set the residual to be 0 at those particular points, pin them down, and that's going to give us the 2 conditions that we need to solve for the 2 coefficients, A1 and A2, that are multiplying our basis function. Okay, that logic is clear? Yep, so we can just work through the math that actually does this, and I won't go in too much detail, but if you want me to back up and do any more of the detail, can do. So in our example, remember we set K to be 1 and Q was 50 e to the x. So this is a situation where we do have the exact solution, but we don't want to use it. And again, just to remind you that our approximate solution is this expansion that looks like 100 plus some amount A1 times our quadratic basis function, B1, plus some amount A2 times our cubic basis function, C2. And actually, let me write that out. It's 100 plus A1, 1 plus X, 1 minus X, plus A2, X, 1 plus X, 1 minus X. Okay, so here's our residual. It's d by dx. The k is just 1, so it's actually second derivative of the approximate solution plus q. So we're going to need second derivative of our approximate solution with respect to x. So the 100 is going to go away from this guy. What am I going to get? Only the quadratic terms are going to stick around, right? I'm going to get a minus x squared multiplying a1. So when I differentiate that, when I differentiate that twice, I'm going to get minus 2a1. And then from this guy here, I'm going to have the cubic term. Is that me beeping? Or that's you? Okay. Is your shoe beeping?
No.
Okay. All right. Cubic term, we're going to have minus x cubed times an a2. So we're going to get minus 6a2 times x coming out, and then the quadratic terms actually drop away in that that last one. Okay, so there's the second derivative of the approximate solution, and you know, again, we've still got these constants hanging around because we don't know what they are yet. So we can substitute that into our expression for the residual, which again is a function of our approximate solution in x, and it's just that second derivative, k is 1 plus q, so it's just going to be minus 2a1 minus 6a2 times x plus q, which is 50e to the x. Okay, so there's the expression for the residual for this problem. So you look at this and you immediately see, well, there's no way the residual can be 0 everywhere, right? There's no way that this linear term, no matter what we choose for a1 and a2, there's no way we can make it equal to 50e to the x for all values of x between minus 1 and 1. So that immediately tells you is that those two basis functions we used are not rich enough to describe the solution exactly, which is not really a surprise, right? But now the question is, what are good choices that we can make for a1 and a2 so that we get a decent solution? And again, what are we going to do with the collocation method? We're going to pick a couple of points for x, and we're going to set the residual to 0 at those points. That's going to give us the conditions, and then we'll solve for a1 and a2. So so if the source was 0, if q were equal to 0, and this were the residual, what would you choose for a1 and a2? You could put them to be 0. So you could make the residual 0 everywhere. What would our approximate solution be then? Yeah, T equal 100. So if you think about the physical problem, if you had 0 heat source and you pinned the temperature to be 100 and 100 on either end, that would be the solution. So there's an example of a source where, I mean, it's kind of a trivial solution, but of a source where you could get the exact solution. Yep. Yeah. Yeah, so it's a good question. So the question is, if we have a Q that basically we can't do the integration by hand, what would we do? And that's a very good question, and we're going to talk about that too. You're going to see some, in fact, you've already seen probably in the pre-reading some of the integrals that show up with Q. If you can't integrate it analytically, there's something called Gaussian quadrature. So quadrature is a way to numerically do integrals that are basically too hard to do analytically. So that's going to be in the pre-reading that's due next Monday, and probably Vikram will be covering it on class, I would say, probably on Monday. So there are ways that basically we can numerically integrate things that we can't do by hand. Yeah. Yeah, so in that case, there's going to be, what you'll see is when we actually get to talking about the finite element method, that there's a bunch of integrals we have to do. By using quadrature, you're going to actually end up having to approximate the integrals, but you'll be doing the integrals over sort of small elements. But yes, the quadrature is going to introduce a little bit of additional error. Yeah. Yeah. Okay, so we have the expression for the residual, and so now what we're going to do is pick n equal 2 collocation points. So again, just to remind you, collocation method says enforce the PDE at n equals 2 points. And enforcing the PDE, what does that mean? Enforce the PDE means, i.e., set the residual equal to 0 at 2, and by points, we mean 2 values of x, 2 points in the domain. And here's our domain. There's x. Remember, we're going from, we chose L equal 2, so it goes from -1 to 1. So there's 0 in the middle. And the collocation points we're going to choose are there and there. That's -1/3 and +1/3. And those are the collocation points that spread things out the most, kind of away from, because we have the boundary conditions here at -1 and 1. So it actually turns out we don't really use the collocation method. It's not a good idea. One of the reasons we're doing it is because it's a good stepping stone to see how the weighted residual works. But that's a good question, because in some cases people do use collocation, and aerodynamics is a good example. And the reason you use the 3/4 chord point is because for a particular kind of lift distribution, that integrates you exactly. And in fact, your question is somewhat related to the question about numerical integration. When we see quadrature, you're going to see it's the same, it's going to be different settings. I don't want to confuse you, but quadrature, when you do numerical integration, we're going to put points in the integration domain, and those points are chosen in a particular way so that we can integrate certain functions exactly. So it's, here they're chosen to be spaced out. There are actually all these rules. They're called quadrature rules. There are all these different kinds of points, and they actually tend to be named after the mathematicians who discovered them, different patterns of points where it says, space things evenly or distribute them out. It's actually a pretty interesting area of study. In fact, Alex, I would say, knows a lot more about these things than I do. Is that true, Alex? What's your favorite set of points for meet quadrature? So depending on the function you're trying to integrate, there's kind of optimal choices of where you might put the points. Yeah. Yeah, something about the solution or something about the basis functions that you're using to represent the solution. Yeah. Yeah. Yeah, so that's a really good question. So if you're trying to approximate things, but there's something in the middle that you would really care about. So now what you're talking about is an adaptive strategy. And again, this is a very current area of research. In fact, a lot of Professor Wong's research that he's, I think, mentioned right at the beginning that uses adjoint methods. So that would be bringing in information that tells you where are the regions in the domain that are most sensitive to what it is you care about. Where might you put more points? People who choose points to do this quadrature or this numerical integration sometimes will choose to adapt in these ways. And, what you would like is you would like kind of general rules that work well, but then you would like to be able to adapt sort of depending on your particular problem of interest. And there are definitely a lot of adaptive strategies out there, but it's also an area that a lot of people are working on. Yeah, good question. So you guys are all ready for the lecture on part on quadrature. And in fact, when we come to talk about Monte Carlo integration, Monte Carlo methods, evaluating means and variances, that's just integration as well. So that's all just about putting points in a domain. And what you're going to see is Monte Carlo does that randomly, but in some cases you can do better by putting them in putting the points in a very specific way. Okay, but here we're going to do just so we're in 1D. So in 1D you can usually get away with pretty much anything. We're going to just put them at -1/3 and 1/3. And so what that means is, again, set the residual. And I'm purposely writing out all the functional dependencies. I keep writing R of T tilde, comma X, because it helps me remember that residual is a function of X. And so what I'm doing here is I'm evaluating the residual at the point X equal to -1/3. That's a point in my domain. So that means substitute X equal -1/3 into my expression for the residual, which gives this 50e to the -1/3, and set that equal to 0. Right, so there's the first condition. And then the second condition is the residual evaluated at +1/3. Again, substitute that in to the expression So we're just changing the sign here, and then this is going to be 50e to the plus 1/3, and that's been set equal to 0. So now you can see we keep sort of reducing the problem. The first thing we did was assume the functions, these guys, that we wanted to approximate the solution in. Then we said we've got 2 degrees of freedom, 2 unknowns, so let's use a collocation method. Let's set the residual to be 0 at 2 points. We chose these 2 points. We've enforced these conditions. Now we have 2 equations, 2 unknowns. We could solve that. You could probably solve that analytically or using Mathematica or whatever you like. And what you find is that A1 and A2 are 26.4 and 8.5. Okay, so those numbers don't mean a whole lot to us, but again, what's the key? The key is that this is our approximation of the solution. So we're saying that by the collocation method, our approximate solution is T tilde is 100 plus 26.4 times something that looks like that quadratic, minus, plus 8.5 times something that looks like that cubic. And when you add those together, you get something that is at least an approximate solution to the PDE. So I want to take a look at what that solution looks like. Well, I put the projector on. Are there questions about the collocation method? If we were actually using collocation method, we would use more than two points typically. It's a nice simple example. So I have a code here that actually implements, I guess I should plug my laptop in. This guy in. Okay, so I have a code here that's going to implement it. There are the 2 basis functions. Phi1 is 1 minus x, 1 plus x. Phi2 is x times that, the cubic. And the collocation method just gets implemented here. It's kind of hardwired because all the derivations have been done, sort of done offline. But let's just run this. We won't run that yet. Okay, so what are the plots that we're looking at here? So here, first of all, is a plot of the temperature versus x. In the solid blue is the exact line. That's the one that we computed analytically for this problem. We can do that. And the dashed line is what we got with collocation. Okay, so it actually doesn't do too badly, right? We sort of assumed this form of the solution, with the solution being 100 plus a quadratic plus a cubic. We figured out, just with 2 degrees of freedom, what good choices for A1 and A2 would be. It's actually not too bad, right? So there's a plot of the actual compared to the collocation's approximate solution. Here's a plot of the error. So that's T minus T tilde. We can compute again in this case because we happen to have the exact solution. You can see that the error is 0 on either end, and you could see from the previous plot that the exact solution, the approximate solution, was always under predicting in temperature compared to the exact. So you see here that with an error being negative. Okay. Now for this problem, we can look at these because we do actually know what the exact solution is. We're not going to be able to do that in general, but what we could plot is the residual. So again, what is this? This is R of T tilde comma X, and we're now taking the T tilde that we determined. We specified the form of it. We chose A1 and A2, and remember it's a function of X. So here's the residual plotted out as a function of X, and now you should be able to see this is where you can make sure you did things correctly. This guy should be 0 where? Here at minus a third, and here at plus a third. The 2 points at which we asked the residual to be 0, and then everywhere else it ends up being non-zero. Yep. Okay, so that is it for collocation method. Good. Any questions? Good, it's clear. All right, so now we're going to talk about the weighted residuals method, the method of weighted residuals. And this is really the method that we want to focus in on, because this is going to be the launching point for finite elements. But again, we were talking about collocation just sort of as a way for you to start thinking about what it means to approximate a solution with a finite number of basis functions, and also to think about there being different ways for you to actually come up with the coefficients. Yeah, Libby. Yep. Yeah. Why that? Yeah. So what do you? Maybe start with the error. Are you happy with the fact that the error is 0 at the endpoint? So let's try to put them side by side. Yep. Yeah, exactly. That's exactly right. So if we start with the error, should the error? Oh, it's still warming up. Yeah. Yeah. Because by construction, the error is 0, right? Because we constructed the basis functions to be 0 at either end. So no matter what value we choose for A1 and A2, the approximate solution will be exact at the boundary conditions. What about the residual? Yeah, say it a bit louder.
You're not satisfied with differential equations.
Yeah, so specifically what do you think's not what it should be at the endpoints? I'll put this up because projectors. So derivatives, yeah, exactly right. So basically it's telling you that, and you can see it physically in the shape, but you can also see it mathematically, because it has this form. When you take the derivative, as soon as you move away a little bit, things are going to go astray because the second derivative's not right. And at the endpoint, the derivatives are not what they should be. Yeah, it's not, with only, now it's come on, we'll turn it off. We've only got 2 degrees of freedom, right? We said the solution is a constant plus the quadratic term plus the cubic term. We've only got 2 degrees of freedom, so you only get to pick 2 things, right, to put them down. And we said, let's make the residual be 0 at -1/3 and +1/3. I guess we could have chosen to make the residual 0 at the 2 endpoints. I don't know what solution. Maybe Alex can quickly figure out in his head what solution that would have been. That would be kind of a bizarre choice, but I'm not sure if that. I'm just wondering if that might give a zero solution everywhere. But you can't kind of have everything. We only got the residual 0 at the -1/3 and the +1/3 collocation point. Yeah. There seems to be a big lag in the projector. There we go. Get it off. Okay, so any other questions about collocation? Yeah, so that's a good question. If you look at the residual, could you tell whether you're using too low of an approximation? In other words, can you tell by looking at the residual how bad the error might be in the solution? And the answer is yes, and there's some beautiful theory. Again, it's going to depend on the PDE that you're talking about. There's theory that basically says that it relates the norm of the residual, how big is the residual integrated over the domain, compared to how big is the error integrated over the domain, and they're related by a constant, which depends on the properties of the PDE you're solving. And that comes back to what I was talking about earlier, that for a nice PDE like this 1D diffusion, it actually turns out that looking at the residual is a really good way to understand what would be happening with the error. For nastier PDEs, that's not so much. But what you're sort of asking about gets to a lot of the theory of the error analysis and the finite element method. That people do a lot of very rigorous analysis of errors based on being able to compute the residuals. And in fact, the residuals also can then start being an indicator for figuring out how to do things like mesh refinement, and all these things are kind of related. And then the theory with our joint methods. So if you're interested in that stuff, you have to take 16920, which Professor Wong will be teaching in the fall, which is the grad class on numerical methods for PDEs. I don't know how much you get into that stuff, Chi, but a little bit more than here. But you have to take that class so that then you can take 16930, which really would get you into it, right? Yeah. Okay, that's good. That's great questions. So now, if you guys are ready, we can talk about the method of weighted residuals, which hopefully won't be too much of a jump from where we are, but it is a different philosophy. So everything is the same up until the point that we define this residual, but where we're going to kind of take a fork in the road is now we're going to use a different strategy for coming up with the two conditions to figure out what those 2 degrees of freedom are. Okay? So same idea, approximating the solution with the basis functions and the expansion. But now what's different is how do we come up with the conditions to determine the functions A1 and A2? And so method of weighted residuals. Okay, so in order to move forward, in other words, in order to define these two conditions, we're going to define something else. We're going to define what's called a weighted residual. Okay, so we defined the residual. It still sits over here, which is the thing that we get when we substitute the approximate solution into the PDE. Now I'm going to define the weighted residual, and I'm going to call it, and actually I was realizing when I was going through that the notation and the notes jumped around a little bit. So let's call this capital R sub I. It's going to be a function of the approximate solution T tilde, but not a function of x, because we're going to integrate things out over x. So we're going to define it as the integral over the domain. And again, the domain in our simple problem is just x from -1 to 1. We're going to take a weighting function, which we'll write as wi. That's a function of x. And we're going to take our residual. You know what? I'm going to give this a little just to make sure that they're different. And it's going to be integrated over dx. So again, little r sub I is going to be our ice weighted residual. And what you're going to see is that we're going to need n of these things. Because again, we're looking for n conditions to find out n unknown coefficients. And it's defined to be the integral of a weighting function, which is our wi, and times this guy here, which is our residual, and we're integrating over the domain here, x going from -1 to 1. Okay, so residual is a function of x, weighted residual is not a function of x because we've integrated over, and the integration is weighted by some weighting function wi. But the weighted residual is still a function of our approximate solution T tilde. Okay, so now what does the method of weighted residuals do? It says, let's choose n different weighting functions, w1, w2, up to wn. Let's define the n corresponding weighted residuals, and let's set each of those weighted residuals equal to 0. Each time we set a weighted residual to 0, we're going to get one condition, right? So we'll do that n times with n different weighting functions, and that will give us the n conditions we need to compute our n a coefficients. Yes? Seems like kind of a bizarre thing to do. It's okay. You guys are so quiet. Does that mean that you think this is very easy or kind of weird? We don't know. So let's write it out a little bit and see. So again, the method of weighted residuals, we're going to require n weighted residuals to be 0. So that means we're going to have to choose n weighting functions those are the W1, W2, up to Wn. They're all functions of x. And we're going to then get, again, n equations to determine these coefficients, A1, A2 to AN. Okay, so first thing we need to do is choose n weighting functions. So this is the first question, is now what do we choose for the WIs? What do we choose here? So the answer is that there's a variety of things we can choose, but there's a very special choice that results in what's called a Collocation method. What does the Collocation method say to do for the weighting functions? You guys read about this. Yeah, exactly right. Let the weighting function be the same basis functions that you're using to approximate the solution. Okay, so the same phi i's, the phi 1, phi 2, phi n that we used, we've erased it now, but that we used in our expansion of t tilde, choose the same basis functions to be the weighting functions that you use to define your weighted residuals. Okay, turns out you don't have to do that. There's a bunch of other methods. There's Petrov-Collocation methods where you can choose different weighting functions, but we're only in this class going to consider Collocation methods where you choose the weighting functions to be the same basis functions that we're using to approximate the solution. So the Collocation method is a very special choice that says choose Wj to be equal to phi j. And it turns out that this choice has really good properties for some PDEs. And again, if you take 16920 with Professor Wang in the fall, you would see how this plays out from an energy perspective. Okay, so this just means the same functions are used to approximate the solution as are going to be used to weight the residuals. Okay, so for our example, what does that mean? That means, coming back to what we were doing before, that means that the first weighting function would be our phi 1, which was 1 minus x, 1 plus x. And the second weighting function would be the cubic, which is x times all of that. And then the first weighted residual, R1, which is a function of t tilde, would be the integral from -1 to 1 of W1 of x times R of t, x dx. And the second weighted residual would be the second weighting function multiplied by the residual integrated over x from -1 to 1. Okay, I don't want to work through all the math on the board, but basically you can see what's going to happen here, right? We're going to substitute in W1 as 1 minus x, 1 plus x. We have the expression for this guy that we derived before that was minus 2a1 minus 6a2x plus 50e to the x. Yeah, so now at that point, it's just multiplying things together and integrating. And you could do it all by hand for this example, or you could, again, throw it into Mathematica or something and get it out. And then what are we going to do? We're going to set R1 equal to 0, and we're going to set R2 equal to 0. It's going to give us two conditions, two unknowns, solve those, and we're going to come out with, in this case, a solution that says A1 is 27.6 and A2 is 8.9. Okay, so I skipped over a lot of the messy math there, but I don't think there's anything conceptually difficult. Two conditions now coming from setting the weighted residuals equal to 0, where the weighted residuals correspond to taking the residual, multiplying it by the basis function, Collocation, integrating over the domain. Plugging through all the math, solving the equations gets us this solution, which says that by the method of weighted residuals, for this choice of the basis functions, the cubic and the quadratic, and a Collocation method, the solution we get is, the approximate solution is 100 plus 27.6 amount of our quadratic basis function plus 8.9 amount of our cubic basis function. Yep. So the different solution to what we got with collocation, right? We got to it through a different route. So I'll pull it up and we can look at that solution and we can compare it to collocation. But first, questions about method weighted residuals. Does that make sense? Yeah, so that's a good question. The answer is going to be it's going to depend on the problem. So there's no general guidelines that I can give you. For this particular level, what you're doing exactly right is that because the what came out of the collocation method, and we'll see it in a second, the residual was, I forget whether it was positive or negative everywhere, but it always had one sign. And we're going to see that the method of weighted residuals actually kind of balances out. Now that's going to make sense, because what are we doing when we take the residual and we weight it and then we integrate it? I think of this as kind of like we're asking the residual to be 0 on average over the domain, but on average weighted by W1, right? Because if this were gone and I just integrated it and set it equal to 0, it would be like saying make the residual on average 0 over the domain. So it's like taking an average but weighting it by W1. So yeah, I'm going to expect this to come out with something that's going to be a bit more evenly distributed rather than with collocation where it had all of one sign. But there's not, I mean, you want to be careful about, I think you want to be careful because it's going to depend on the problem. You'll see when I stick the plots up in a second that it actually turns out our residual will be 0 at a particular point X, not because we set it that way, but that's how it comes out. So another sanity check would be to go back and plug that point in and make sure that the residual, if you're worried about getting the integration wrong, take that point X, plug it in, and make sure that indeed the 0 is satisfied. But I said earlier, we don't really use the collocation method, but we do use method of weighted residuals, and it's going to be because it actually turns out to have really great properties. It wins for this problem, and that's not really a coincidence. And in fact, it forms the basis of what we're going to do with the finite element method, which is incredibly powerful. Okay, so I'm going to run the same script that I ran before, but now I also have the implementation of the weighted residual method. So here are, so this is the combination of all those integrals over there amount to the stiffness matrix, well, this K here, this matrix, and the coefficients being K inverse times B. So all the integrations amount to that. And so we're going to run it and plot. So let me clear all, close all. Okay, so just like we looked at before, we can look at the temperature as a function of x. Solid line, just like before, is the exact solution. Dashed line is the method of weighted residual solution. So remember, we've got the same degrees of freedom as we had for collocation, right? Still only 2 degrees of freedom. And same basis function. The only thing we've changed is the way we choose how much of each basis function to put in. And you can kind of see visually, I'll put them both up together, but you can see visually it does pretty well. And actually what Kevin was just observing, it's not always under. It actually is under a little bit here and over a little bit there and then under a little bit. Yeah, that's kind of just the way it came out for this problem. So there's the temperature compared to the exact solution. We can look at the error as a function of x again because we have the exact solution here. And again, we can see it's negative, then it's positive, and then it's negative. And we can look at the residual. And so now, remember with collocation, what did we see? We saw with the collocation method that the residual was 0 at the collocation points because those were the conditions that we imposed to get the coefficient. Here, it turns out that the residual is 0 at minus 0.4 and at plus 0.5, but that just kind of fell out. And again, if you're looking for a check to make sure you did the integrations right, you could always take your residual, substitute in whatever these values are, and make sure it came out to 0. But again, that just fell out. What we actually asked for was that this residual, when weighted by this guy and then integrated over the domain, is 0. And this residual, when weighted by this guy, the cubic, and integrated over the domain, that is 0. Yep. And so then finally, let's see, plot the comparisons. So I put them all on the same plot. So there in black is the exact solution, the red is the method of weighted residuals, the blue is collocation. Turns out method of weighted residuals did better for this problem, but again, you want to be careful about making general assumptions. They both have the same number of degrees of freedom. They only differ in the choice of those coefficients. Here's a plot of the different errors. And again, I would say the method of weighted residual is kind of more balanced, again, because we're asking for this weighted residual to be 0. And then lastly, here are the plots of the residuals as a function of x. And now you can see clearly what I was just saying. There's the collocation pinned to 0 at the collocation point. The method of weighted residuals happens to be 0 at a couple of other points. Okay. More questions? I'd say it's really important that you feel very comfortable with the method of weighted residuals. The idea, and maybe, let me just say it again, the idea that we're going to take the PDE. We're not going to mess around with the derivatives. We're going to instead say, let's approximate the solution and an expansion with a finite number of basis functions. We're going to choose the form of the basis functions, and today we've been talking about polynomial basis functions. Now we need to figure out a way to determine the coefficients, how much of each basis function. And so the way we're going to do that is choose weighting functions, and with the Willcox methods, we'll choose those weighting functions to be the same basis functions that we're approximating the solution with. We'll weight the residual with the weighting function, integrate it over the domain, define the weighted residuals, set those equal to 0, and get the conditions we need to find the coefficients on our expansion. Yep, all those steps. And what we've done today is define global basis functions, right? So my phi1 was a quadratic that varied over the whole domain, and my phi2 was a cubic that varied over the whole domain. Finite element method, you're all ready for it now, is just I guess kind of a simple but really pretty, huge next step, which is to say, let's not do this on the whole domain. Let's divide the domain up into little pieces, and let's use this idea. Let's define basis functions, special basis functions that are polynomials just on the little pieces. Yep, and we're going to have coefficients that go with those. Yeah, Trent. Yeah, so that's a good, so in that case, the weighted residual, we're going to see all that on Wednesday. So what's going to happen now is that this weighted residual is actually going to have very special structure, because the way we're going to define the basis functions is that they're going to be local on elements. That's the finite elements of finite element method. And so when we do the integration, a whole bunch of it is going to disappear, and we're going to be integrating locally just over the elements. But what you're going to see is that there ends up being a little bit of interaction between one element and its neighbors because of the way the basic functions are going to come out. So we'll work through all those integrals. I think you read maybe a little bit of it already. How far did you guys get in the reading? You saw the linear, the nodal basis? Yeah. But yeah, we're going to work through all of that, and you'll see that's what's incredibly powerful with the finite element method, is this idea of using a polynomial basis and a local element. We're going to get these integrals with so much structure that we can handle. It's going to sort of all work out in a really neat way. That's exactly right. We're still integrating the weighted residual over the whole domain, but a whole lot of it's going to go away, and it's going to turn out that we get sort of these special patterns that show up because of the way we choose the basis functions, and you'll see all of that. Yeah, we'll do all of that. I think on Wednesday we'll sort of work through all the steps of the finite element method and have you go along and do it. So actually bring your laptops if you can, so you can do some stuff on that lab. Okay. Yeah, Ben. Yeah, that's a good question. That's a good question. The question is the fact that the method of weighted residuals, the resulting residual crosses 0 n times, is that a coincidence, or is it always going to happen? I think that's it's a very interesting question, and I'm actually not sure, because I was wondering, actually, is there a way to figure out where we could have put the collocation points for this problem? We could have put the collocation points in a particular point and gotten the same answer that we got with method of weighted residuals, and it's going to have something to do with the 50e to the x that's in the forcing function. I suspect the fact that it crosses twice is not a coincidence. I think it probably has to cross twice, but I don't, yeah. You feel like it's kind of like the fundamental theorem? Maybe it's a great question for the final. Really good final questions are when the professors don't know the answer. What do you think, Chi-Chi? Yeah, well, the thing is, we have an expression for the residual, which we wrote out, which was, what's the expression for our residual? It's minus 2a1 minus 6a2x plus 50e to the x. So I guess you could figure out how many crossings are possible because of the degrees of freedom that we have. Yeah. Yeah. It actually turns out that even though things seem like coincidences, there are almost no coincidences. And these kinds of problems, it's usually that there's so much structure in the problem that you could have, but yeah. Okay. If you have, if there are parts of the method of weighted residuals that are a little bit uncomfortable for you, I would strongly suggest you talk to me or to Alex or to Chi-Chi or to Vikram before Wednesday, because otherwise things are going to get dramatically worse for you on Wednesday. Make sure that that's why I went kind of slowly through this lecture, is because it's really important that you have all these steps kind of clear in your mind. And please, if you have a chance to even just listen to a few minutes, especially those of you who said you like the audio recording, if the combination of what's on the screen and me talking is good enough, then I can keep using the Blackboard, but if not, please let me know.